and we shall understand how it is exactly applied in the coming slides. Okay, so basically we have understood that we want our computer to detect the presence of objects. Fine. But how do we actually store this data? Our computer does not isn't like humans, right? It is not able to perceive and understand images. It can only understand numbers. So we store the data of the presence or absence of the object numerically. How do we do that? We will basically store it in a form of an array where one value represents the probability that the object is present or not. So if an object is present, maybe the value zero point 0.9 or 0.95, like the probability will be stored. The x and y coordinates of the bounding box. This is basically the bounding box, and we'll basically store the x and y coordinates of this box. And if we are dealing with multi-class object detections, that is a number of different types of objects are present, we'll also store the class value. How do we do that? So basically in the image of a street where there are people and cars as well, if our computer detects the presence of a human being, it will store the value 1 corresponding to the class person, and it will store the value 0 corresponding to the class vehicle, which basically tells us that okay, this object is a person and not a vehicle. Okay, so now let's dive deep
Hello,
into.
Aditya.
Yeah,
Yeah, actually, there was some issue with the YouTube live stream. So, could you once repeat the last part again? I guess after the use cases of object detection, whatever you are explaining, if you can just repeat it again for the YouTube viewers.
yeah, sure. Okay, so
All
after
right.
our
Okay.
yeah. Okay. So now that we have understood the use and practicality of object detection, let us just understand that how does computer store our data. Basically, computer doesn't understand whatever image the image data is, right? It can only understand numbers. So we are going to store the data of the image numerically. How do we do that? Basically, we'll store it in a form of an array where one value represents the probability of an object being present or not. So basically, if an object is present, the value 0.9, 0.95, maybe 1 can also be stored, which will indicate the probability of the object. Second will be the x and y coordinates of the bounding box. So this is our origin, and we'll store these values, which will basically tell us where the object is present, right? So our second objective gets satisfied. Our third objective was to determine the class. So basically, if we are dealing with multi-class object detection, and like in the previous image where we saw that there were people and there was vehicles on the street. So if the computer detects the presence of a person, it will store the value 1 corresponding to the class person, and it will store the value 0 corresponding to the class vehicle, which basically tells us that this object detected is a person, right? Okay, so now I'll be explaining two algorithms which are widely used in object detection. We want to understand that how does an object detection model actually work. So let's understand how. Har cascades. So Har cascades is basically an algorithm which is widely used in face detection because it is able to detect the presence of objects in the image irrespective of their scale and location in the image. So basically, when we have when we provide an input where there are faces, irrespective of whether of what the size of the face is in that entire image and what its location is, our algorithm will be able to detect the presence of faces. It is an extremely easy algorithm to understand and implement, which makes it widely useful. Um, One question that arises is that how do we provide the input? What is the input that we provide to our Har cascades algorithm? Our Har cascades algorithm naturally has a lot of images provided as input, but it has positive and negative input images. Now, what do we mean by positive and negative input images? Positive images are the ones. So if I am applying it for face detection, our positive input images will have a lot of faces of people. So the presence of faces will be positive input image, and negative input images will be random images which do not have faces. So basically, when we are on this data set, our model will be able to classify whether an image contains an object or not. So basically, we are providing images both having faces and not having faces, and we are training the model to just tell us whether a face is present in the image or not. Okay, so this technique was developed by, is also known as Viola-Jones face detection algorithm, and it introduces a very novel concept which is called as Haar features. So what is a Haar feature? We basically saw that an image is nothing but a grid of pixels, right? So a Haar feature is basically a rectangular grid of, is basically a rectangular kernel. Now this rectangular kernel will will have pixels. Say my white region corresponds to pixels of intensity say 0, and my black region corresponds to pixels of intensity say 1. So this is nothing but a grid of pixels. All these the pixel values in this region are 0. The pixel values in this region is 1. Similarly, when we look at this Haar feature, the pixel values of this, what is the size of this rectangle? Is it 18 cross 20 or 100 cross 250, or what is it exactly? So the answer is that there is no fixed value of the size. We train our model using various Haar feature sizes, and then basically narrow down upon certain best Haar features of specific sizes. We'll see how we do that. Okay, so how are Haar features basically applied on the image? Consider this rectangular patch to be an image which is converted into grayscale. For my convenience, I have assumed that all the pixel values that are close to white are close to 0. So white is corresponds to the value 0 and black corresponds to the value 1. And these grayscale pixels will have different pixel values depending upon their intensity. So what I do is I place,
Aditya?
yeah,
Yeah, your screen is not visible. Can you check once again? Probably unshare and share again. That should help.
okay.
Yeah, now it works.
Is my screen visible now?
Yeah, now it is visible.
Okay. Yeah. So I'll place this Haar kernel on this patch. Now what I do is I take the sum of all the pixels that lie in this black region and all the pixel values that lie in this white region. After that, I just take a difference of these pixel values. That's it. That's basically the algorithm. But how is it working? You might be wondering. So basically, what will happen is I'll set say a threshold value. Now in this case, let us assume that threshold value is 1. Okay. So I'll take the sum of the pixels in this entire region. I'll take the sum in this region and I'll subtract. After subtracting, say if the value is quite large, say it is close to 1, then it means that all the pixels in this region have a considerably high value as compared to pixels in this region. What does this mean? It means that all the pixels in this region are close to the color black. All these pixels are close to the color white. It basically means that we are able to detect the presence of an edge. So when we move from left to right, an edge will be present on this region. Basically, we are able to detect the presence of an edge using this algorithm. So once we set our threshold value, and if we are able to see that the difference in the sum of the pixels is large enough, we basically are able to understand that, and there is a huge amount of difference in the intensity of pixels in this region, and hence there is an edge as we go from left to right. So there is a vertical line that is present here. Okay, but how are we using this to detect faces? Our Har features will travel over an image in this way, as it is seen in this GIF image. So our features will be of varying sizes. As you can see in this image below, this feature, the rectangular feature, corresponds. So when I allow my rectangular feature to traverse in this direction, it is able to detect the presence of an edge in this part, which is nothing but the eyebrow of our image. Similar with this rectangular feature. As we traverse as we traverse the rectangular feature over this entire image, the rectangular feature is able to successfully detect the presence of an edge, that is the eyebrow, in our image. This Har feature is able to detect the presence of the nose because this region is a bit darker and this is darker and this is lighter, which is exactly how our Har feature looks like. Even in this part, the teeth are white and the region below is dark, which basically corresponds to our Har features here. So that is what we do. We pass our Har features over the entire image and are able to detect the specific features that are present in that are facial features that are present. So like the eyebrows, eyes, nose, the teeth, etc. So after we pass these Har features, we are able to narrow down upon certain features which have the maximum ability. As you can see, this particular Har feature is able to detect the presence of eyebrows extremely accurately. In place of that, any other Har feature, if I use this Har feature, it might not be able to detect, it won't be able to detect the presence of this feature, that is the eyebrow, right? So we are basically able to narrow down upon Har features of specific sizes that are able to detect the presence of features in our image. Okay. Now we saw that we are taking a sum and then taking a difference of those sum, etc. Fine. But it's fine if we have an 8 cross 8 or 10 cross 10 image, maybe. But what if we have 256 cross 256 image and our Har feature is extremely small? How does it, won't it be extremely time consuming and cumbersome? We need to come out with a faster and simpler method to calculate that, to make our calculations much easier, right? That's what we do when we calculate the integral image. The integral image is also a concept that was proposed in the paper. So what do we mean by the integral image? We are basically just going to transform our original image into a new type of image, a new grid of pixels. And what are we going to what are going to be the pixel values in this integral image? So for this image, what if I choose say 0.2? I'll just replace this value with the sum of this with all the pixel values that lie to the left and on top of this 0.2 pixel. So basically, let's suppose I am taking the pixel 1.0. So I'll replace 1.0 with 1.0 plus 0.3 plus 0.4 plus 0.7. If I'm taking 0.5, I'll just replace it with 0.5 plus 1.0 plus 0.3 plus 0.4 plus 0.7 plus 0.9, which is nothing but 3.8. So what I'm doing is just condensing the entire. I'm just taking the sum of all the values in this matrix and storing it in the rightmost bottommost pixel. So in our image, the sum of the pixels of the entire image will basically be stored in the rightmost bottommost pixel, which is this. So how is it going to help? Okay, so consider a previous example where we are basically putting our Har kernel on this. We are calculating this sum and subtracting it with this, the sum of this, right? So let's suppose we place our kernel on the integral image. Now, this particular value 0.1 will be replaced by the sum of the pixels of this 7 cross 7 matrix, which is this. I have marked it here. So this 7 cross 7 matrix, the sum of all the pixels in this matrix is nothing but 26.3. And the sum of the pixels in this 7 cross 4 matrix is nothing but 15.3. So if I subtract 26.3 and 15.3, I'll just get the sum of this 7. I'll get the sum of this matrix, right? From this matrix, I'm able to subtract this matrix, this 7 cross 4 matrix. So I'll get the sum of this 7 cross 3 matrix. Now, what I do is I'll subtract this value, that is 4.6. So I'm basically subtracting this, the sum of all these pixels from our current sum, right? But what I've done is I have double subtracted this region, if you see. So what I'll have to do is I'll have to add the pixel values back into our sum. So I'll add 2.7. So what we have done is we have reduced our calculations to just three three operations, two subtraction operations and one addition operation. That's it. That makes our calculations much easier. Our 8 cross 8 matrix might not give justice, but if I have a 100 cross 100 matrix, you'll see that this is a very fast method and it reduces our computation, right? So this is basically the way we use the integral image to calculate the Har value. Okay. After we simplified our lives by using the concept of the integral image. But can we make our lives more easier? Because understand that there will be so many Har features. Even if we use the integral image, there are so many Har features on which we have to train our model. Rather than doing so, is there a simpler method to do that? The answer is using AdaBoost method, which is an ensemble learning method. So we have covered AdaBoost in our previous sessions, hence I won't go into detail as to what AdaBoost actually does. I'll just show how it is used in this method, in this algorithm. So what we do is we create weak models. We basically run our Har features on smaller training data set, and we create we create small models which are actually weak models. We call them weak learners. So what they're able to do is they are not able to classify images with a very good accuracy, but then we combine them, which is again the principle behind AdaBoost, that we combine all our weak models to create a strong model, right? So we combine the results of these weak learners to create a strong model that is able to give us our results very accurately. So basically we are able to extract all the important Har features that are necessary for our face detection method. Okay, so let's understand what is meant by the term cascade exactly. Why is it named as a cascade? So what we do is, say we have a set of Har features that we are able to narrow down upon, and say we have one Har feature. So what we'll do is we'll place the Har features in their decreasing power of or decreasing ability to detect objects. So the Har feature which is present at the first position, is extremely useful in object detection. Then 2, then 3, then 4. Then we basically pass the image through these Har features in sequence. If our first Har feature is not able to give us a positive output, that is not able to detect a feature in the image, we completely discard the image. Thus, so basically our most powerful Har feature has to be present so that we're readily able to discard the image which does not give us a positive output from this Har feature. If we get a positive output, that let's suppose the Har feature present here is able to positively detect the presence of a feature in the image, we pass it on to the next one. The next is able to detect, then we pass it on to the next one. If this is not able to detect, we completely discard it. We don't pass it forward. The image which reaches till the end has has an object, so we are able to, if the image reaches till the end, we can say that the object has been detected positively. So we are able to detect the presence of object. Okay. Now let's take a short quiz to test our understanding. Just scan this QR code. Yeah. I hope the QR code is visible. Just scan this and please start the quiz. Also, you can post any of your doubts in the Q&A. The QR code is on the right. The left QR code is for the quiz, and the right one is for the Q&A. Yeah, I'll wait for a few more seconds. Yeah, I'll start the quiz. Okay, I'll lock the voting in 5 seconds. Okay, so there was a considerable voting for the fourth option as well. So basically, the thing is that Har features are of varying sizes, but for any image, our set of Har features will not be the same. Because in any feature, let's say we are using it for face detection, our different images will have different face sizes, right? So we'll have to train. So while training the model, the Har features will be of different sizes and will depend upon the image. So C option is correct. Okay. Now let's look at a code implementation of Har cascades for face detection. Okay, so I have made all the necessary imports, and basically this CV2 IM Show is the compatible version with Google Colab that works for showing the image. Then the thing is that OpenCV has made things a lot easier, and there are built-in functions and libraries which are used for face detection, eye detection, nose detection, etc. So if you go to their GitHub, you can readily get these functions. So that's what I've done. I've just used this har cascade frontal face default.xml as my cascade classifier. So our face detector will just store this. It will read the image, and I'll have to convert it to grayscale as it is only able to understand grayscale images. So I'll convert it to grayscale, and then this is nothing but the detect multiscale is basically the function that runs the entire thing. So what is this 1.3 and 5? This is nothing but, so 1.3 is basically the scale factor. It is just parameter that we want our image. So basically, we'll in this algorithm, a small patch will be used uh, for detection at a time, right? Our hard features will detect the presence of features patch by patch. So we are just specifying the size. And 5 is basically the min neighbors, which is a parameter which specifies how many neighbors that how many neighbors that the candidate rectangle should retain. So these are commonly used values 1.3 and 5. So I have used the same. Now, uh, for for this code basically gives us the bounding box. This is nothing but the bounding box. So this will basically give us, so x plus w and y plus h are these coordinates. X comma y is this coordinate, and 00255 is nothing but the RGB value. I wanted it red, and 3 is basically the width of the rectangle. And then we use CV2 IM show to show us the image. Yeah, so it is able to successfully detect the faces. Okay. Now let's move on to our second uh, algorithm, which is used in object detection. This is called a histogram of oriented gradients. The name sounds very fancy and complicated, but it is quite simple. Okay. So what is HOGs? HOGs are nothing but a feature descriptor. So a feature descriptor, so let's understand this, that when we look at an image, like, or when a computer looks at an image, there are multiple parameters or multiple uh, things that are present in the image, right? Like the color, there are different colors, there are edges, boundaries, etc. Now, understand that all of this is not necessary in object detection, right? We only need certain information, certain parameters that are useful in object detection. So feature descriptor does just that. What it does is it extracts all the useful information and it discards all the extra information. So it basically converts the image into a feature vector. So h cross w cross 3 is nothing but height, width, and 3, which is the number of channels R, G, and D. So it converts it into a feature vector, which basically provides us with the important information that is present in the image. The HOG does the same. It is a feature descriptor which converts an image into a feature vector, and that has 3780. How does it have 3780? We'll look into that. Okay. So after so in a HOG, basically the we obtain a distribution. So this distribution is in the form of a histogram. This is basically the histogram, and this distribution indicates the direction of the gradients, basically oriented gradients. This basically explains how it is named histogram of oriented gradients, because we obtain a histogram of the direction of the gradients in the image. Now, what is gradients in the image? We'll come to that. So What I wanted to understand is HOG algorithm, it does not actually classify the objects in the image directly. It is just a technique that is used to obtain all the important information in the object. We'll use it for further processing. Okay. So what is a gradient? So if we have a function of multiple variables, so gradient is nothing but a vector gx comma gy. So gx represents the partial derivative of f with respect to x. So what is the derivative? Derivative is nothing but change in f with respect to x, and partial derivative is change in f only with respect to x and not with respect to y. So gx is nothing but del f by del x, and gy is del f by del y. As gradient is a vector, the magnitude is given by this formula, square root of gx square plus gy square. And the orientation is nothing but the angle that it makes with the x-axis, positive x-axis. That is given by tan inverse of gy by gx. Okay, now we know that how gradient works for functions, for multivariable functions. But how does it exactly work for images? Okay, so say consider this pixel, 85. So gradient in the x direction will be nothing but the difference of pixels in the x direction. So 89 minus 78, which is 11. Or in case of y, gradient in y direction will be 68 minus 56, which is 12. Subsequently, we can calculate the magnitude and the angle and store it in two different variables. So it's pretty easy. The gradient is nothing but, what does gradient essentially indicate? It indicates change, right? So 89 minus 78 is nothing but the change in x. 68 minus 56 is nothing but the change in y. Okay. Now, after we obtain the gradient values, we group the pixels. We group the pixels in 8 cross 8 matrices. So we basically consider an 8 cross 8 matrix of pixels to be one, like we are grouping it, and then we distribute these grids in bins. Now, what are these bins? Say I have a 0, 20, 40, 60, 80, 100. So these are basically storage boxes, as we can call it. And we store gradient magnitudes in them. So usually, like even in this paper, the number of bins specified was 9, ranging from 0 degrees to 180 degrees. 0, 20 degree, a 40 degree bin, 60 degree bin, 80 degree bin, and so on till 180 degree, right? And so step size is naturally 20, which is 180 divided by 9. So what I want you to understand is, why have we taken it from 0 to 180 and not 0 to 360? So we consider the gradient, the negative value of gradient to be positive. I mean, we take the positive value of the gradient only. We don't take the negative value. Hence, our angles we can only vary from 0 to 180 degrees. Now, what we'll do is we'll basically store gradient magnitudes in these bins, okay, corresponding to the gradient directions, like gradient angles. How are we going to store it? Let's just see that. Say this is the matrix of gradient directions and this is the matrix of gradient magnitudes. First, let's just focus on this. I want to store this value 2 in these bins. Okay. The corresponding gradient direction is 80. So we have an 80 bin. So we just directly store the value 2 in this bin. Okay. Now, one question might arise is, what happens to the angles? What happens to all the other angles except these? How are we going to store? So if I have, say, this 4 is the gradient magnitude and 10 is the gradient direction. So it will lie in this bin or this bin, or it has to be distributed in these two bins, right? So distributing it equally also will not be very effective and fair to do, because I mean, in this case it turns out to be equal, but equal distribution is not a very good idea. So what we do is we multiply the magnitude with a particular weight and then store it in this bin. How do we calculate the weight? The weight is nothing but this angle subtracted by this angle. So 10 minus 0 divided by 20, which is the step size. I'll take this difference divided by the step size and multiply by the gradient magnitude. So 10 minus 0 divided by 20 into 4, which is nothing but 0.5 into 4, which is 2. So intuitively, if we are trying to understand why are we subtracting, are basically determining how close is 10 to the value 0 and divided by the step size. That is how we are determining the weight. So similarly for this, so 20 minus 10 divided by the step size, which is 20, into 4, which is 2. So weight is just the parameter that determines how close it is to the nearest bins. Okay. So we store these weighted values in these bins and convert this matrix into just 1 cross 9 matrix. I mean, a 1 cross 9 array of values, right? So after that, we just keep on adding and we obtain a histogram. This will just represent the magnitude, the total magnitudes that is stored in each of these bins. So this, if this is 0, 20, 40, 60, 80, 100, 120, 140, and 160, what is the total magnitude that is stored in this bin will be represented by the histogram. So what we are doing is we are converting an 8 cross 8 matrix into just 1 cross 9 matrix of value, a 1 cross 9 array of values. So we are basically able to condense the information that is represented by an 8 cross 8 matrix into 1 cross 9 array, right? After that, we combine 4 8 cross 8 matrices to form a large 16 cross 16 matrix, right? And then we just store all the values in a 1 cross 36 array of values. After we store, basically, after storing this array, we divide it by the magnitude, which is called as normalization. What is meant by normalization? We are just dividing each feature vector. This is called as a feature vector. So we are basically dividing each feature vector by the magnitude of the feature vectors. This is mainly done to reduce the variations in the values, right? So this will make our computation, calculation, etc. much easier, right? So this is how we are able to normalize the values and we obtain a 1 cross 36 feature vector. Okay. So now in the paper which introduced the concept of HOGs, a standard image of 64 cross 128 was used. If we use 8 cross 8 pixel grids, we obtain 8 such grids along the width and 16 along the length. So we'll basically require 7 boxes along the width. So 1, 2, 3, 4, 5, 6, and 7. So we'll require 7 boxes along the width and 15 blocks along the length. And so we'll get 15 into 7, that is 105 feature vectors. We saw in the previous slide that each 16 cross 16 feature vector will store 36 values. So what we are able to do is we are able to store 36 into 105, that is 3780 total values so we are able to store 3780 values, and thus in this way we are able to obtain that number 3780 as I had said. So the HOG feature descriptor will store 3780 values. It will just extract the important information of the image and then we'll use it to and then we'll provide the input to a different model, like say a classifier algorithm, like say an SVM classifier algorithm, and we have seen how SVM classifier works. So basically that SVM classifier will be able to then detect the presence of an object. So in this way, histogram of oriented gradients is able to extract important information. It is mainly an image processing technique used to take in all the important aspects of the image and then we provide that input that to our classifier algorithm and then we are able to detect objects. Let's go for another quiz to test our understanding. You can scan this QR code and then 1 second.
Lima Pogo.
You can scan this QR code.
Sir. So, cash ah?
I'll start in a few more seconds. Yeah, I think I'll start with this. Yeah. Yeah, so in this question, the 40 bin and 60 bin, this basically means the 40 degrees and 60 degrees. Subsequently for all the other options as well. Um, One second, I think I'm mistaken. The last option should be 2.5 in the 60 bin and 7.5 in the 40 bin. I think so. Yeah. Yeah, basically the last option is only correct. No, the values won't be stored in the 40 degree and the 80 degree bin because the 40 degrees and the 60 degree bins are the closest ones. So the values will be stored only in these bins. Okay. So now let's move to the code implementation of HOGs. Yeah. First, we'll look at how HOGs are implemented from scratch, and then we'll just look at how things become simple using OpenCV. So these are basically all the imports that are necessary for implementing the code. We are basically converting our image. We are basically converting our image into grayscale and resizing it as well to the appropriate parameters 128 cross 64. Then we have two arrays, magnitude array and the angle array. So let's understand this part of the code. What have I done here? Why not? So basically, in the image, if I reach the there's some noise, I think.
அட பேன் கண்ணம்பல போடணும்னு இருந்ததுடா. நானு இவன் டிரைவர் போ அப்படின்னா என்னன்னா
Someone's mic is on. Can you please mute? It will be very convenient. Yeah, thank you.
வச்சிருக்கான் அது.
Okay. So now if we see, so what have I done is, in our image, say I have reached the leftmost portion. Okay, I'm calculating the gradients for the leftmost edge. How do I do that? Because there's nothing on this side, right? So what I'll do is I'll assume a 0 pixel to be present on this side, which is called as padding. It is the concept of padding. So what I'll do is I'll assume a 0 pixel to be here. So if I have this pixel, okay, and I'm calculating the gradient for it, I'll subtract this minus 0, which I assume is present here. Okay. So this I think adding, and this is the corresponding code for this. So this is the GX for the left edge. This is the GX for the right edge. And for all the images in the middle, it will be the standard formula that the right pixel minus the left pixel. Similarly for GY, if I reach the top layer of pixels, I'll just assume that a 0 pixel is present on top of this, a 0 pixel layer is present on top of this, and I subtract 0 minus the bottom pixel value. Okay. Now, basically the magnitude is nothing but the magnitude of the gradients, and I'll just append the array of magnitudes. This is basically rounding it off to decimal places. After that, I calculate the angle and store it in an array. I convert this into NumPy arrays, and I just basically try to plot what it would look like. So the image corresponding to the magnitude of the gradient, and this is the image corresponding to only the angles of the gradient. So I have this, then I specify the number of bins and the step size. These are basically three functions which I'm using to calculate what value will be again, someone's mic is on. Can you please mute yourself? Yeah. Okay. So basically, we are just these three are just functions to calculate in what bin we shall store and what will be the corresponding value. So you can see magnitude into Cj minus angle divided by step size. This is nothing but the deciding the weight that will be stored multiplied by the magnitude. That's it. And this is our array of 9-point histogram. So it will traverse. I've kept a step size of 8. So basically, I have grouped these pixels in 8 cross 8 boxes, and I'll then run this part. So I'll take the magnitude and angle for each block, and then using this function, I'll just calculate the bin in which I have to store it. Which bin should I actually store? So basically, for this code, the reference is taken as the gaps, that is 10, 30. I mean, we have 0, 20, 40, 60, 80 as the bins, right? What is done in this code is 10, 30, 50, 70. These are taken as the reference values, and in we have considered this values to be our say jth bin. So basically the indexing also starts from 0, and so the 0th bin will be the one corresponding to the value 10. The first bin will be the one corresponding to the value 30. But you can change your referencing as well. I mean, I've just done this for the convenience. So I'll store using the calculate vj function. I'll just store this value in the bin, in my jth bin, and in the next bin. So say if I have some angle, and say if it is between 0 and 20, I'll decide what value I'm going to store in 0, and in the next bin I'll store the next value, which is calculated by the magnitude value minus vj, right? So in this way I'm just storing these values in different bins, and I'm using this to create our histogram. And this is basically the normalization part. So as you can see that I am just dividing by the magnitude and storing it in our final feature vector, basically combining different 8 cross 8 blocks into one feature vector, which will basically store all those values. This is just a compilation type of thing, you can say that. So basically it is a tensor which will store these values. So HOG number of HOG features will be nothing but 15 into 7 into 36, which is 3780. Now all of this, I mean, HOG is quite extensively used, so you don't want to code all of this every time you are writing something, some object detection code, right? So OpenCV has made our life simpler. It has just provided a built-in function HOG, which runs on the same on this very idea. And again, these are the necessary imports that you have to do. skimage.feature from this library we import HOG, and we print the shape and just resize it again for our convenience. So after that, we pass it through the HOG function. Now our HOG function will take these inputs. So it will take the resized image. Orientation is equal to 9 basically means the number of bins. So it automatically determines the step size by dividing 180 by 9 when we specify this. The pixels per cell is nothing but how are we going to group? We are going to group in 8 cross 8. Cells per block is nothing but we are going to further group our 8 cross 8 into a 2 cross 2 matrix, that is 16 cross 16, right? So we'll take 4 8 cross 8 blocks to form a 16 cross 16 matrix, which is nothing but a 2 cross 2 block. So this is nothing but that. And after that, we'll just use this function and it will output this HOG image. And let's just try and plot it simultaneously. So this is our input image and this is our HOG. So what is this exposure.rescale intensity is nothing but how bright do we want these white things to be. You can set it, you can keep a larger range and this will become much brighter and the dark will become much darker. So nothing, it's not very important, I mean, it's fine. And we are just plotting these two images, and we'll just save it as output.png. This is basically how your histogram of oriented gradients will look like. This is nothing but the important information that is there in the image. As you can see, the borders are the things that mainly matter in object detection, and that is what we are going to extract. Yeah. So this was it from my part, from my side. I introduced you to hard cascades and HOGs. And Rutvik, should I share the attendance QR code now? Hello? Okay, one sec. I'll just share the attendance QR. Yeah. You can use this QR code for your attendance. I'll keep it on for a few more minutes to so that you can give your attendance. Yeah, one person has raised your hand. Yeah, you can ask what's your doubt. Okay. Yeah. I hope all of you have marked your attendance. Um, yeah. I've allowed you to unmute those who have raised your hand. You can. You can speak if you have.
This is a wrong code. This is for Slido.
Slido, sir.
Okay.
The QR code you have given is not for attendance. Please check the
Oh,
QR code.
okay, okay. One sec. I'll just check. Hmm, I think Jyotiraditya, if you have the QR code, you can share it because I'm not able to find the attendance. So I'll stop my sharing and then you can maybe share. Yeah,
Sure, I'll do that.
yeah, fine. Okay. Please mute yourselves if you don't have any doubts. And Jyotiraditya will share the QR code. Don't worry about that. That's it from Jyotir. You can carry on from here. You can share your screen, share the attendance QR, and continue with your session.
Hello.
I hope you guys are able to see the QR code. Just let me know if this is the working one.
It's working.
Yeah, fine. You can then mark your attendance using this QR code.
If you guys are done marking your attendance, I'll stop screen sharing. You guys can take 5 minutes of break and we'll start off at 6:10 with the second part of object detection. So guys, we'll be starting off. I hope that my screen share is visible.
It's not visible very clearly, Jyoti. Can you try again? I mean, it's compressed.
What about now?
Bit better. Yeah, fine.
Is it okay now?
No, it was okay. It was okay a few minutes back now. Yeah, fine.
Hello guys, and welcome to part 2 of the session 8 of summer school by the AI Club IITM. I am Jyotiraditya, and this is Object Detection 101 continued. Today we are going to be covering two revolutionary object detection algorithms. One, the RCNN, which stands for Region-Based Convolutional Neural Network, and the second, YOLO, which stands for the You Only Look Once algorithm. So far, when if you guys have attended the previous session, we have trained convolutional neural networks to perform tasks like classifying objects, usually only identifying which of the given classes the object might belong to. Say you have trained a convolutional neural network, it will be able to identify within a given image a single object and which class that object belongs to. However, many modern CV tasks require us not only to identify which class that object belongs to, but they also require us to locate where exactly the object is in a given image. By any means, they want us to draw a outline around that object in the image to know its location. This is where the algorithms that I'll be teaching you today will come into the picture. Uh, we will first cover the YOLO algorithm, and YOLO once again stands for You Only Look Once. The YOLO algorithm is basically a well thought culmination of a few ideas that we will look at now. One being the bounding box predictions, two being the sliding window and its convolutional approach, three the IOU or the intersection over union, four anchor boxes, and five non-max suppression. The YOLO algorithm basically takes the best of these five ideas, and then puts them together to make a very quick object detection algorithm. Let us first look at the idea of object localization. Given an image, the goal of object localization is to algorithm. It is to learn the class of the image and where it is located in the image. Basically, when we have this cat, the goal of object localization algorithm is to output that this image is a cat and output this red outline drawn over it, which we call the bounding box. For an image, for a given image, we divide it into a grid of say 19 by 19. That is, we draw a grid on the image which is of size 19 by 19. In each grid cell, we define a target variable as shown. The target variable is used in almost all object detection algorithms. It has some components. The first one being P, the probability of an object being present within that given bounding box. This is sometimes also referred to as your confidence score. Xmin, Ymin, Xmax, and Ymax, but then we mostly write them as Bx, By, Ph, and Pw. Px and Py would be representing the geometric center, that is the geometric center's coordinates of the bounding box. Bh and Bw would be the length and the height of the width or height of the bounding box. Here we have two classes C1 and C2. Whenever we have only two classes within the target variable, one of them would indicate the presence of the specific object, and one of them would be for the boundary or the background. But whenever we have multiple classes that we want to detect, C1, C2, C3, and so on, we will have those many target values, each of them representing which class the object might belong to, and the last class representing that it belongs to none of these. Whenever we train our model or over a bounding box regression algorithm, the input target, that is where we want this y to go to, would be something like this with p1, because we know that the ground truth of the object being there is 1. The x coordinate and y coordinate of the center of bounding box, the length and width of it, and which class it belongs to. And the predictions would be something like this. Here, as you can see, it is not the we don't know the ground truth probability, but we are actually predicting a confidence score. That is, the prediction feels that there is an 80% chance of the object being present within itself. These are the x and y coordinates. These would be the height and width. And this is showing that it belongs to the class of a car. C2 would be the class of the background in this case. Now let us have a quick recap over a concept called max pooling. Max pooling involves running a pooling window over the entire image. It outputs the value of the pixel within the pool having the maximum value. Max pooling has two advantages. One, it helps us downsize the image to a required dimension. And two, it also helps us retain the most dominant features. Why do we need to do max pooling? Let us say that we have trained the convnet, that is the convolutional neural network, to accept an input of a specific size, say 2 by 2. And we have an image of say 4 by 4. Max pooling would then take, in this window, it would take the pixel having the maximum value 8. Here 6, here it will be 9, and here also it will be 9. And that would be the in, and this output would essentially be the input that we would be giving to the convolutional neural network. Max pooling is thereby helping us reduce the size to a required size, and it is also at the same time not losing any features that the convolutional neural network would need to take up. Have a look at this video which shows how max pooling works. As you have seen, max pooling helped us reduce the size of the input image to a convenient size. It also retained most of the important features. That is, it is still visible to an observer that it is a 7. Have a look at the GIF here. This is essentially what the sliding window technique is all about. This was used as the first draft towards an object detection algorithm. Uh, The sliding window technique is a highly useful technique in object detection algorithms in order to get to the target vector y which we defined before. We first decide a suitable dimension for the sliding window. In this GIF, we have seen that there is a green box that is sliding over the entire image, and this green box's size is what we are referring to as the dimensions of the sliding window, and the number of pixels it is moving over every time is defined as a stride. So in the sliding window technique, we first decide a suitable dimension for the sliding window, and then we also decide a proper stride. Taking this stride, we move over the image, and every time it moves over the image for the specific window of the image that it is covering, it is returning the target vector. The target vector is essentially whatever we have defined before y, which contains the probability of an object being present there, the center, and height, width, and which class it belongs to. What we have seen essentially here in the next part of the GIF is that the size of the image decreased, but that is essentially a visualization in which we are increasing the size of the bounding box. We then continuously increase the size of the bounding box and we get the output bounding box predictions until we get the best window prediction. So say for example, you have a convolutional neural network that has been trained over a 14 by 14 by 3 image. The 3 here stands for the red, blue, and green components. When you pass each sliding window through over this image, you take now 16 filters, each having size 5 by 5. This would generate 10 by 10 images, and because we have passed 16 filters, each of them filters passing over the input image would generate a feature map, and we have 16 of such feature maps. Uh, then we do max pooling as previously discussed. Max pooling with a 2 by 2 size and a stride of 2 would reduce this 10 by 10 feature maps to size of 5 by 5, and the number of feature maps are still undisturbed. We then pass these 16 feature maps through 2 fully connected layers, each having 400 nodes, and finally through a softmax. The softmax helps us predict the object to be among one of the 4 classes. What essentially the sliding window technique does is, whenever it passes over the image, it takes each sliding window and it applies this entire operation for each and every sliding window. Say you had an input image of size 200 by 200 by 3, and you had a and your convolutional neural network was trained such that it requires an input of 14 by 14 by 3. So your your sliding window would essentially have a size of 14 by 14, and we would take a slide of 1 because we do not want to lose any features. Or when you calculate the number of such sliding windows obtained, we would see that it is a very huge number. Uh, so, as you guys must have already figured out, the sliding window technique is inefficient because it is taking up a lot of time to go over each sliding window, send it over to the convolutional network. And every convolutional network that we use in these object detection algorithms has already been pre-trained over tens of thousands of images or belonging to the object class. Uh, and now we will be looking at something called the convolutional implementation of the sliding window. What exactly does the convolutional implementation do? Instead of applying the filter, what we have seen is the sliding window technique takes the one part of the input image, passes it through the convolutional network, and then gets an output. What if instead of doing this whole part, that is the feature maps, placing them over the input image, we place them initially. That is, we apply the feature maps over the whole input image, and when we take the windows, that is what is our convolutional implementation. So when we look at the convolutional implementation for a input image, that is the same image as seen before, the 14 by 14 by 3 size, after the initial filtering part and the max pooling part, instead of passing it through 2 fully connected networks, we take their equivalent by passing 400 filters of size 5 by 5 to get an output vector of size 1 by 1 by 400. So essentially, we are replicating the fully connected layer that had 400 nodes by passing 400 such filters, which have been pre-trained obviously to capture the same features as the fully connected layers did. And then here, instead of passing 5 by 5, since the size of the tensor here is 1 by 1 by 400, we pass 400 1 by 1 filters to replicate the second fully connected layer. And then we pass 4 1 by 1 filters, which is replicating your softmax operation. Now let us say we had a 16 by 16 by 3 image. The sliding window technique would tell us to take 14 by 14 by 3 image 1 from here, a stride of 2, 14 by 14 by 3 image here, the 14 by 14 by 3 image on the bottom left and the 14 by 14 by 3 image on the bottom right. On such a small image of size 16 by 16 by 3, we can see that we are generating 4 images with a stride of 2. When the image size becomes large, like 28 by 28 by 3, you can imagine the number of sliding windows that would need be required to be generated. The convolutional approach, however, is able to do it in a single step. What the convolutional approach says essentially is you pass the filters directly over the image as shown, the 400, not 400, 16 5 by 5 filters. Then you'll get a output vector of size 12 by 12 by 16. You then max pool it with 2 by 2 filters to get a 6 by 6 by 16. You replicate your fully connected layers with 400 5 by 5 and 400 1 by 1 feature to get an output tensor of 2 by 2 by 400. And then you pass 4 1 by 1 filters, which is replicating a softmax operation to get a final output vector of 2 by 2 by 4. There now, the convolutional approach essentially says that the output vector, this 2 by 2 by 4 vector, the 4 is inside the page, can be interpreted as the concatenated tensor that contains all the information required to the 4 images. That is, the top left would be this blue dot, the 1 by 1 by 4 on the top left here. The top right would be this one. The bottom left would be this one, and the bottom right would be this one. Therefore, we can see that instead of doing it over, instead of taking the sliding window, passing it over the input image multiple times, and then for each passed image doing the entire convolution, if we apply the feature maps on the entire input image, we will get an output tensor which has the softmax probabilities for each of the sliding window as shown. The usefulness of the convolutional approach, the advantage is becoming apparent as the size increases. So when we take a 28 by 28 by 3 image, we are getting an 8 by 8 by 4 output tensor. So as you can see, if you take a slide of 2, you'll get 64 such sliding windows would be required. Passing 64 such through the convolutional would take a lot of time. However, when you do the convolutional implementation of the sliding window, the final output is directly an 8 by 8 by 4 tensor. And when you take the corresponding image, its corresponding output tensor can be directly picked up from here. Let us move on to the next idea. That is intersection over union. While training the model, let us say that the model is predicting that the purple box is what it feels is where the car is present. And we know that the ground truth prediction, not the prediction, the ground truth is the red box. What can you use as a parameter to measure the effectiveness of your prediction? That is, you need something to measure how good of a prediction that this box is. Enter IOU. IOU scores is a way of measuring the accuracy of the predicted bounding box. Higher the IOU score, better is the prediction. IOU is basically the area of the overlap of the two bounding boxes, that is this intersection part, divided by the area of the union. An IOU of 1 is indicating that the predicted bounding box and the ground truth bounding box are the same. There are some general IOU thresholds that have always been in use. An IOU less than 0.5 or 0.6 in single classed images. That is when your input images are containing only one class and you get an IOU score of 0.5 or 0.6, it would imply that the prediction, that is your bounding box prediction, is poor and can be discarded. However, an IOU less than 0.3 would imply that the object, when you have multi-classed object, that is your input image has more than one object. An IOU less than 0.3 in this case would imply that the predicted object does not belong to the class that you're looking for. Let us say that a grid cell contains the centers of a human and a car, and you have two bounding boxes. One of them is for the car, one of them is for the human. Uh, if the algorithm predicts that the IOU score is less than 0.3, it is inherently telling us that when we are trying to predict bounding boxes for the human, the box with which you are measuring the IOU score does not belong to the human, and it is essentially indicating the presence of another object. So this is bringing up a very interesting question for us. What if a grid cell contains multiple object centers, or what if the algorithm is detecting the same object with multiple boxes of different sizes? We have the concept of anchor boxes that help us to choose which one of the bounding boxes would be the best prediction. Anchor boxes are a set of predefined bounding boxes of a certain height and width. These boxes are defined to capture the scale and aspect ratio of specific object classes you want to detect and are typically chosen based on object sizes in your training data sets. So as you can see, for this image, we have four predefined anchor boxes: the blue, the green, the golden yellow, and the bright yellow ones. We can inherently understand that the golden yellow bounding box that I'm outlining right now is the best initial bounding box on which you can train your algorithm to predict that the cat would be in such a bounding box. You are usually allowed to define several anchor boxes, each for a different object size. Anchor boxes can be essentially viewed as fixed initial boundary guesses. And anchor boxes also solve the problem of multiple object centers being in the same grid cells by allowing us to modify the target vector as shown. So let us say we have two anchor boxes. Instead of getting an output vector of size 8 that goes into the page, now we would get an output vector of say size 16, that is 8 into 2. The first 8 target values, that is the probability, bounding box coordinates, and the classes, would be representing those with respect to the first fixed anchor box, and the second ones would be representing those with respect to the second fixed anchor box. We go over to the next idea, which is called non-max suppression. We technically require a criteria to eliminate all the overlapping bounding boxes, while we also want to select the best bounding box. We also need to take care of the fact that we don't want to lose out on those bounding boxes that are essentially not related to the object we are looking for, but they are indicating the presence of the object belonging to another class. This is where non-max suppression comes into place. Non-max suppression is a computer vision method that selects a single entity out of many overlapping entities. That is, of these predicted bounding boxes, now the three-step algorithm that I'm going to tell you in the next slide, that's non-max suppression. These three steps will help us to decide which one is the best one, and also will help us to decide which bounding box that we are not supposed to lose upon. Step one, say after running the convolutional implementation for this image, you got the following bounding boxes. The first step would be to select a threshold, let us say 0.6, and remove all bounding box predictions that have a confidence score less than this threshold. So 0.6 would translate to a confidence score of 60%. So we are removing all the bounding box predictions that have a confidence of say less than 60%. So we feel that any bounding box that has a PC less than 0.6 is not accurate enough. That is a threshold of your choice. Step two would be to take the bounding box having the maximum confidence score. That is, in the case of the human, step two would be to take the green bounding box, which has a maximum confidence score of or PC value of 0.96, that is 96%. Now you run the IOU algorithm with respect to all the other bounding boxes that have predicted the human there, and you remove all the bounding boxes that have an IOU greater than 0.5. What does this imply? Uh, the removal of all bounding boxes that have an IOE greater than 0.5 is essentially removing all those bounding boxes which are not the best fit to the human, but they have also predicted this human as their probability. And this method is also ensuring that you're not removing those bounding boxes with an IOE less than 0.5. The bounding boxes that had an IOU less than 0.5 with this green box would be indicating the other objects that are not belonging to the class of humans having sharing the same center with the same grid cell as the human. Step 3. Now you have the bounding boxes. Let us say you have C classes that you want to predict in the entire image. One being a car, one being a dog, and one being a pedestrian. So you have to run the non-max suppression algorithm C times for every output class to finally get to this output. Now, putting together all the ideas that you have hopefully learned, we now take a look at the YOLO algorithm. What YOLO essentially does is, according to the research paper, YOLO divides the input image into a grid of cells 19 by 19. For each grid cell, YOLO predicts multiple bounding boxes based on the fixed anchor boxes and also their associated confidence scores. These bounding boxes are representing the potential detections of objects. Additionally, YOLO is also predicting class probabilities, that is the PC value that we have defined in the target vector for each of the bounding box to determine which class it may contain. So, for example, if we have this image that we have divided it into a grid of 3 by 3 for simplicity, the YOLO algorithm in its initial run, for each grid cell, it would predict multiple bounding boxes based on the anchor that we have given. If you have a close look at the image, you can understand that we have given two anchor boxes. One is a horizontal rectangle that is having a longer length, and one is a vertical rectangle that has a longer height. So in each of these grid cells, it has predicted the presence of an object with two bounding boxes. In the next step, we have to apply the non-max suppression. Why do we do this? Because we want to reduce the duplicate and overlapping detections and also keep the most confident ones while also making sure that we don't lose out multiple object detections. As we can see here, the preliminary steps of the non-max suppression have removed all the non-confident bounding boxes from the image. Here we had many, and here we have only four bounding boxes. All four have their centers. These two have their centers as the human. These two have their centers as the car. The further steps of the non-max suppression algorithm remove all the predictions with IOU greater than 0.5. So we get the best bounding box possible. And they remove all the predictions with IO greater than 0.5 with respect to the bounding box that has the highest PC value. The final output image that we show here will have the final set of the most confident bounding boxes along with their corresponding class labels and confidence scores. So this is essentially the YOLO algorithm. This is what the YOLO research paper has to say. You take an input image, resize it, the input image, run the convolutional neural network and the non-max suppression algorithms, and you get a final output vector like this, which is giving you the bounding box with the class label, that is a pedestrian, a dog, and also the probable confidence scores. There is a data set that is available on the internet. We call it the Picasso and people art dataset. But when we train the YOLO algorithm on this data set, it is able to produce fairly accurate results. And YOLO is basically a state-of-the-art algorithm because of the fact that it is able to do everything in a small amount of time. If you look at all of these images, you might notice a small exception. In this image, if you recognize it from the Fast and Furious series where Roman is jumping from one car to the another, you can see that it has wrongly classified him as an aeroplane instead of a human. This is because the YOLO algorithm would have some specific feature set that on which it was trained, in which it understood that whenever I look at an image and I see these specific features, I will understand that it is an aeroplane. It does not essentially identify that a man who is midair and flying is a human and he's not an aeroplane because that is not on which it is trained. But the YOLO algorithm, this is one of the very few inconsistencies with the YOLO algorithm. That is, in these specific bizarre cases, it as an aeroplane instead of a human, or else the YOLO algorithm is a very beautiful algorithm. It is able to detect objects with a high with a proper class labels and a high accuracy. I now have a small question for you guys. Scan this QR code in the slide. Just tell me whether the QR is visible or not. I hope the QR code and also the Slido code, if it doesn't work for you, are visible. Hello.
Yeah, it is visible.
Okay, fine. I'll wait for a minute or two. Uh, Also, let me know if the quiz is working or it is still stuck in level. Most of you have given the right answer. YOLO is you only look once. It's not you only learn once, which me and my friends do before the examinations. And it you only look once is because of the fact that YOLO algorithm is essentially doing all of its computations in one go over an input image. YOLO is not processing images multiple times. YOLO is processing the entire image in a single way because of the convolutional implementation of the sliding window. YOLO is not designed for image segmentation tasks. YOLO is designed for object detection tasks. So, moving on. Now that you've seen YOLO, let us look at the RCNN, the region-based convolutional neural network. If you look at this hierarchically, RCNN came into existence before the YOLO algorithm. But RCNN is an old and obsolete algorithm, and it has many of errors that were solved by further algorithms, and YOLO is the most recent one. YOLO is the one that works better with real-time data, so that's why we covered it first. So RCNN is basically a region-based convolutional neural network. RCNNs detect object via region proposals. Instead of using the sliding window approach over the entire image, RCNNs have innate algorithms that help us generate region proposals, which can then be sent to convolutional neural networks. There is one innate region proposal algorithm that RCNN uses, which is called the selective search, under which the underlying algorithm is called the greedy algorithm. Uh, Let us say that this is our input image. An initial subsegmentation of the input image is generated using the methods that are described in the paper Efficient Graph-Based Image Segmentation by this guy. So what is meant by subsegmentation? By taking some kind of similarity considerations, we are grouping together pixels that fall under these similarity considerations, giving each of them a specific color so that the entire image can be segmented in this form. And this is where the 3D algorithm comes into picture. From a set of two regions in the subsegmentation as shown before, you choose two that are the most similar. Here we calculate similarity scores between the two regions based on characteristic features like color, texture, size, and fit. And then we then take these two regions. If they meet our similarity considerations, we combine them into a single large region. We repeat the above step for multiple iterations. After we do that, when we do that for multiple iterations, we see that they're going to take some sort of a phase. That is, they start making sense. And we measure the performance of the greedy algorithm using a metric called MABO, which is mean average best overlap. So this is the input image. This is what is happening after the initial segmentation. For each segmentation, if you use a bounding box, this is what the bounding box predictions would look like when placed over the input image. After a few iterations of the greedy algorithm, the bounding box predictions, we see that they are improved. And also that the segmentations seem to take some sort of a shape with this blue one representing the television and this representing the face of the woman. After many iterations of the greedy algorithm, we get the final image as shown. The selective search is taken up. The selective search traditionally generates up to 2000 region proposals per image. Each of these region proposals is warped. By warping, I mean that it is resized and adjusted for required size. If we take this region proposal, and it does not fit the required input for our convolutional neural network, we then warp the region proposal to a required size. The paper says that we warp it to a size of 227 by 227 pixels, and then we send these warped images to the convolutional neural network for feature extraction. The output is then predicted using a support vector machines. And we train each support vector machine for an individual class, and then we send the bounding box predictions to the support vector machines where it will be fit in one of them. This is essentially what the RCNN algorithm does. This is what the original research paper has to say. You have an input image. By using the selective search algorithm, you are extracting your region proposals. You're warping them to a certain size because you want to fit them in the convolutional neural network. You compute your features. Using the extracted features, you then use the support vector machines that were trained initially to fit somewhere, and then you classify them using the support vector machine. Drawbacks of the RCNN algorithm. One, training is a multi-stage pipeline. What do I mean by this exactly? RCNN is first fine-tuning your convolutional neural network. Then it is also fitting the support vector machines to each of the class based on the features of the convolutional neural network. These SVMs are acting as your object detectors essentially, instead of using softmax. And also, you have to train your bounding box regressors, which will essentially help us get the best fit. So, because we are doing multiple stages, here the training is a multi-stage pipeline, which is essentially taking a lot of time. Therefore, the second point, training is expensive in space and time. Because we are training support vector machines and bounding box regressors, the features that are extracted from each object proposal will be written to disks. When we have very deep neural networks, the convolutional neural networks which are used to uh, obtain the features like VGG16, this process takes up to 2.5 days for around 5,000 images. And these features also would require hundreds of gigabytes of storage. So therefore, the training is very expensive in space and time. And object detection, that is the algorithm in itself, is inherently slow. After training, detection with a VGG16 convolutional neural network takes 47 seconds per image on a GPU. So that is a very slow, because practically we want the object detection algorithm to be able to detect an image within fractions of a second. Getting but when it takes 47 seconds per image, that is a huge drawback. Getting over these drawbacks is the fast RCNN algorithm. The fast RCNN algorithm, essentially what it does is, just like how the convolutional implementation of the sliding window is able to calculate entire features in one single go. Here we have an analogous thing that is happening. What happens here is we have an ROI pooling layer. What is the ROI pooling layer? ROI is the region of interest. So you take your image, you apply the ROI pooling layer on it and pass it through two fully connected networks to get an ROI feature map. And this ROI feature map is also including your region of interest predictions. So you have some regions of interest. It is pooled into a fixed size feature map, and then it is sent through some fully connected layers. And then this feature map is used as the input for the softmax output and also the bounding box regressor. So essentially, this algorithm, the fast RCNN algorithm, is able to do just like what the convolutional implementation is able to do in terms of time, saving time. This also saves a lot of time, but it still has its own drawbacks. What are the drawbacks? Slower training. Though the detection speed has comparatively and hugely improved, when it takes around 47 seconds per image on a VGG set, it takes around 2.3 seconds per image for a fast RCNN algorithm. The training phase here is still relatively slow because we are still relying on the selective search algorithm for the region proposal method. The second drawback is spatial misalignment. What is spatial misalignment? When the fast RCNN uses an ROI pooling layer, sometimes the pooling layer can potentially cause information loss. And when you have information loss and the feature map isn't able to extract these required features, sometimes you're not able to predict the object correctly. And also a single stage detection. Because it is the fast RCNN algorithm is performing the region proposal generation and also the object classification in separate steps, it is not as efficient as a two-stage detection algorithms which are used in faster algorithms. let us go over to the next algorithm that was proposed by scientists, which is called faster RCNN. The faster RCNN algorithm is a two-stage detection algorithm, unlike the fast and the non-standard RCNN, which are single-stage detection algorithms. Instead of using the selective search algorithm and its greedy proposals, the faster RCNN algorithm is using an RPN, which is a region proposal network. It uses this region proposal network to propose the regions that are to be sent to the convolutional neural network for object detection. The faster RCNN is able to gain in terms of time because of the fact that it is able to share convolutional features with the connet that it is using for training classifying objects. So basically, you can view the faster RCNN algorithm as an equivalent of the fast RCNN algorithm that has been merged with the region proposal network by removing the selective search algorithm. This is what the original research paper has to say. As you can see, we take the input image, we apply the convolutional neural network on it, and we generate some feature maps. These feature maps that are generated by these convolutional neural networks are used both by the ROI pooling layer for classification, and they're also used by the region proposal network for generating the proposals that will then be sent over to it. So, because it is a single unified network for object detection, it is able to do it at a very quick rate because of the fact that it is both the ROI pooling layer and the RPN are sharing their convolutional features that they have learned till now. There's some statistical data that is describing how these algorithms perform in real time. Pascal VOC 2007, released in 2007, also in 2012, is a data set that has lakhs of images on which most of the object detection algorithms are usually trained. The first column here is showing on which datasets they were trained. The second column is showing the map scores. Map scores are essentially an intricate scoring way in which you are able to judge how effective your algorithm is. And the FPS part is frames per second, which is able to show how many number of images is the algorithm able to classify in a single second. As you can see, the RCNN fast and fast RCNN do not even come in real-time detectors because the RCNN is detecting 6 frames per second, the fast detecting half a frame per second, and the fast are detecting 7 frames per second, which is relatively slow when compared to the YOLO, which is detecting 21 frames per second. Because these are on less than real time. On real time detectors, the fast YOLO is able to detect 155 frames per second, which is essentially showing that by far YOLO is the fastest algorithm, which is able to do everything in a very small time. This is the QR code for the attendance. You guys can scan it if you have missed it before. So guys, thank you for attending the session 8 of the summer school hosted by IIT Madras. We hope you guys enjoyed it, learned a lot, and also hope that you attend the upcoming one. If you have any doubt, I'll share the Slido link within a minute. You can post your doubts on that, or you can unmute and ask.
Yeah, those who have doubts can raise their hand and we'll unmute them and you can ask your doubts. If you don't have your doubts, thank you for attending. That this is the end of the session.
This is the Slido link for doubts. Thank you all for attending. Have a nice day.
Yeah, Rishi, you can stop streaming now also.